This video discusses the bypass circuit in detail. Just like it says, the bypass circuit bypasses the water from the discharge side of the pump back to the inlet side of the pump. It does this because the pump is actually putting out more water than is actually needed. Now, this is not happening all the time. It's only happening when the call for output humidity is low, meaning we're calling for humidity on zone 1, 2, and maybe 3. Now, this bypass function is performed through the use of a regulator, which is right here. And we'll move into a close-up of that right now. And here it is a little closer. It's this device right here. Now I'm going to zoom in a little closer and describe to you what's going on here. The pump is running and it's discharging high pressure water into this line right here, and it's going through the check valve and out to the zones through this line right here. Now when the pump runs at its minimum RPM, which we'll get to in a minute, it puts out more water than it needs to supply zone 1, 2, and maybe 3. There's 1, 2, 3. So we've got to do something with that excess water. Again, this pump is running at minimum RPM. So what happens is the water goes through this solenoid, which I'll talk about in a little while, and it goes through this line right here, again, stainless steel braided line, into this regulator. And this regulator regulates particular pressure on the discharge side of the pump. So that as the pump rises in RPM, rises in pressure, there's more water that's needed on the discharge, so the pressure continues to rise to the set point of this particular bypass regulator, which is 900 psi, maybe a little higher, 930, 940 psi. So as soon as that pressure gets that high, a spring-loaded valve opens up and starts to let a little water through this line, and it comes around and goes back into the input water supply. If you remember in a different video, this is part of the input water supply. Here's a solenoid, and here's the water coming in. So to put it another way, the pressure builds too high for the zone capacity that it's calling for. We just don't have enough nozzles out there to handle all the water that the pump will put out. So excess water goes through this line right here, it comes into this input. Pressure is controlled right here at 900 psi, and the little bit of water that's excess comes back in and goes into the input and recycles back around. Now I talked about minimum RPM of the pump. There's actually two minimum RPMs to consider when you're running a pump like this. The minimum RPM of the motor, which is somewhat a theoretical value that the pump manufacturer has, and minimum RPM of the pump itself, this guy right here. Both of those minimum RPMs can vary depending on conditions, environmental conditions. When you run this pump motor at a very slow RPM, it is not cooled properly. There's actually a fan back here that blows water through this little fan vent across this motor. And the slower the motor goes, the less air that goes across here. But on the other side of things, the slower the motor is, the less energy you have to put into it in order to make it go slow. And also the other variable is the surrounding temperature, the environmental temperature of the area of this whole pump assembly. So it's really hard to say what the minimum RPM that this motor can withstand. Some people say it's 15 hertz. 15 hertz is actually the RPM that you start to get a sufficient airflow from the fan that's on the back here to get some air to move across here. Some people say it's 10, 8, 5 RPM. Again, that you can run it probably down at 5 RPM, but then the climate here has to be pretty cool or at standard room temperatures. If it has a cool surrounding, this motor can cool by itself a little bit easier. If it was very warm in this environment, this motor would warm up too much. But let's just say that you can feel the difference between operating it at 15 or 20 hertz compared to operating at 5, 6, 7, 8 hertz. I have operated this motor at 8 hertz for quite a while, and you touch the housing and it is quite warm. If you bring it up to 15 or 20 hertz, the air movement across it from the fan cools it a bit, and it is cooler. If you operate it at full load, full capacity, maximum current going through it, it's going to warm back up again. But at 60 hertz, the air blowing across it is pretty great. And that has the ability to take the heat away. The other variable is the pump itself. What is the minimum RPM rating of this pump? This is a Danfoss pump, and Danfoss says that the minimum RPM this pump should be operated at in a continuous mode is 1,000 RPM. The maximum RPM of this pump is 3,000 RPM. At 3,000 RPM, you get maximum capacity out of the pump. So in order to get close to maximum capacity or maximum capacity out of this pump in the United States, we use a 3,600 RPM motor. There are 2 3-phase motors basically available, a 1,750 RPM motor and a 3,600 RPM motor. So if you're using a 3,600 RPM motor here and the minimum RPM of this pump is 1,000 RPM, that equates to 15 hertz on this motor is the minimum RPM. Now this 1,000 hertz that they're talking about is at maximum pressure, which is 1,400 psi. So they want 1,000 RPMs, not 1,000 hertz, 1,000 RPM at 1,400 psi. Now this pump is water lubricated, and in order to get the proper lubrication at 1,400 psi, you need 1,000 RPM. Now we are running at a lower pressure, between 600 and 900 RPM. And I tend to believe, and it's not a proven fact, and in fact I can't get it out of Danfoss, that we can run this motor at a lower RPM if the pressure at it, the discharge pressure, is lower. And it all boils down to life expectancy of the pump. Not so much the motor, the pump. Danfoss recommends you examine the internals of this pump after 8,000 hours. Well, if it's running fine after 8,000 hours and there's no appreciable noise, excess noise that's going on in the pump, why inspect it? And if you do inspect it and you find something wrong, like a piston shoe is a little loose or the valve plates are a little worn, the parts to replace them are so expensive within this pump, it just doesn't warrant repairing this pump. So the way Danfoss has pricing on the parts within this pump, it's almost a disposable unit. Now there is another way to look at this. I have this type of system here installed in a customer's facility, and I have 11 of them installed. So I have 11 of these pumps running. And those 11 pumps have been running for 2.5 years in varying life cycles. And I've had 3 of them go bad for a variety of reasons. One of them due to run hours, the other due to some other failures that were facility generated, let's say. So I was able to take all 3 of the bad pumps that I had apart, lay them on the bench, examine them, and actually take pieces from different parts of different pumps and put it back together and get one good pump out of it. So if you have a lot of these pumps, you can piece them together to repair them. And then if you purchased some spare pistons and shoes and maybe a valve plate and some gaskets and things like that, again, they're pretty expensive, and have those on hand, you can actually piece together repairs from the variety of pumps that you have on hand. There are 5 pistons in here, and if one of them is bad where the shoe is worn, where it starts to slop within the shoe, you can just replace that piston. You don't have to replace all 5, and you can get that pump back in a serviceable manner with a minimum amount of noise that's coming out of it. Because when one of those piston shoes gets loose, it starts to make a bit of noise in there, and you wonder what's going on. Let's take a look at it and let's repair it. So again, if you have a lot of these pumps, you can find some semblance of repair for them. So back to minimum RPM for the pump and the motor. I've been running these systems at around 11 to 12 hertz on an average and that equates to about 700 RPM. And that 11 or 12 hertz gives enough cooling through the fan across the motor and satisfies my need to get enough internal lubrication on the components in here to produce minimum wear because of speed and because of lubrication qualities of the water itself. Now, since these are humidification systems in clean room environments in the northern climates of the United States, specifically Minnesota, these systems run at a low out capacity a lot of the time. In fact, these systems provide humidification just about 7 days a week, 24 hours a day, 365 days a year. Within a clean room, there is a demand for humidity just about all the time. Within a clean room, they want to keep a minimum of plus or minus 2.5%. This system has been keeping it at a plus or minus 1%. And one of the reasons these systems run so much is because within a clean room, there's a constant need for cooling. There's a lot of high-tech test equipment in there, and cooling is needed like computer rooms because there's a lot of computer equipment in there and high-test manufacturing, etc. So cooling is required, which does dehumidification to a slight degree for the humidity levels that they want, which is around 45%. So as you cool, you do dehumidification, and the system runs a lot to rehumidify the air to the desired level of 45%. So I said that this system runs a lot, just about all the time, and much of the time that it is running at a very low capacity. So much of the time that this system is running, and I'm going to say around 50% of this time, it's at minimum capacity, zone 1 or zone 2, which is 10% or 20%, and this bypass circuit is in operation. So this bypass circuit is critical. Typically 12 hertz on this pump is enough to supply the first 3 zones or the first 30%. So we are in bypass operation for the first 3 zones. Once we get to the 4th zone, now we're requiring enough water, enough humidification that this pump cannot run at minimum RPM anymore. So we're not going to be bypassing water anymore. So as the 4th zone calls, the pressure actually drops because we cannot supply enough water to all the nozzles. So that's when the variable frequency drive starts to kick in to increase the speed of this motor to keep the pressure up. Now that brings us to the point of what this solenoid here is for. This is a normally open solenoid valve, so it will let water up to the point of where this regulator is. And when we're in zone 1, 2, and 3, we need this solenoid open to have this regulator function. So in zone 1, 2, and 3, with this solenoid open, we could actually adjust this particular regulator to the pressure that we want, maybe between 500 and 900 psi. That gives us the ability to control the capacity, maybe to precisely tune the capacity to a desired output at low demand levels. Then as the needed capacity increases, as the output demand gets higher, more and more zones start to come in, and we start to need to regulate the speed of this particular pump to keep the pressure up. And at that particular point, we can close the solenoid valve and not use the bypass anymore and regulate the pressure up higher than we could if we had the solenoid in and using the regulator. So at 12 hertz, and when we get to zone 4, we need to start regulating this motor. We can close the solenoid, and now we can regulate this motor to higher pressures, which dictates higher capacities and gives you more precise capacity control. If you didn't have this solenoid in, you would have to set this regulator up to a value higher than the highest pressure that can be generated under the variable speed operation which you're controlling at, and I control at 900 psi max. So that means during the low stages, stages 1, 2, and 3. Without this solenoid, I have to set this regulator at above 900 psi. If I put the solenoid control in here, I can actually have this regulator set down to 800, 700, 600, 500 psi to get varying capacities out at lower stages of operation, and then use the solenoid to turn off the bypass and then do higher capacities at higher stages of operation. Now you might say that you could just go into the air handler and actually change out the nozzles and put in smaller or less nozzles. Yes, that is true, but sometimes you can't go into the air handler because it is a clean room. You are restricted to the amount of times that or when you can go into the air handler. This gives you the ability to give you some more control over the output capacity at lower stages of demand. Now that pretty much concludes what I wanted to talk about here. That is some pretty complex theory on how this thing works. Hopefully I explained it well enough. I get the feeling sometimes I didn't, but then when I re-listen to what I relook at the video that I made, I say, yeah, that sounds like it makes sense. So hopefully this does make sense because again, it is a pretty complex theory of operation for this bypass circuit. So that's it for now. Look forward to putting together next video for you. Thank you for watching. Have a good day.